The learning goals for this worksheet is primarily to determine the limiting reactant and reactants in excess in solutions using molarity, but also to teach you a little bit about various measures of concentration and how to do some conversions, dilutions with them. So there are 6 different kinds of measures of concentration that I'll discuss. The most important one by far is molarity. And then next you have molality. It's very similar, still mole solute, but it's instead of per liters of solution, it's per kilogram of solvent. Now, for the case of water and small concentrations, like less than 1 mole or 1 molal, they're very similar. But molality is important for colligative properties like freezing point depression and boiling point elevation. And then mole fraction is moles of X, whatever X is in your case, divided by the total moles in the mixture. This is important for vapor pressure problems, which is described by Rolle's law. And then percent by mass, percent by volume. These you would see at the pharmacy or the grocery store. You'd also see them in the stockroom sometimes. So percent by mass is when you're concerned about the purity of a solid mixture. So it might say 95% sodium bicarbonate or 99% sodium chloride. So that's just saying that out of 100 grams of that substance, that mixture, you're guaranteed to get 99 grams if it's 9%. And then percent by volume is a similar idea, but it's by volume. So it's saying 80, if it's 80%, 80% mils out of 100 is this pure substance. And then you've got per ppm, parts per million, ppb, parts per billion, ppt, parts per trillion. They're typically used in air, water quality context, but also if you're concerned about a particular impurity, you might see some chemical bottles that say less than 5 ppm or 5 ppb, and then state a specific impurity. And that's just guaranteeing that certain impurities have been especially tested to be below a certain level in that mixture. So we have an example here for concentration. How many grams of sodium hydroxide are needed to make 500 mils of 0.1 molar sodium hydroxide solution? This is a pretty typical kind of calculation you would have to do later on in the course. Of course, you'll need the molar mass of sodium hydroxide, so I've calculated that off here. There's 1 sodium, 1 oxygen, 1 hydrogen, so you just add up their atomic masses and you get 39.997. To do this conversion, we start off with 500 mils, the volume we want. We convert it into liters and then multiply it by 0.1 molarity. Notice that moles over liters instead of molarity is what I've written there. And then moles of sodium hydroxide cancels moles of sodium hydroxide, and that leaves us with just the grams. So if you multiply all of those together, you get 2 grams. Excuse me. So note that there's 2 significant figures there for the 2 grams because the concentration here is 2 significant figures. For dilutions, you always use this formula. M1V1 is equal to M2V2. Now this is important for any time you've got a very concentrated solution in the stockroom and you want to dilute it down to get a concentration you're going to use in an experiment. So you've got M1 and M2. These describe the initial and final concentrations. They can be in whatever units make sense for your problem, And then V1 and V2, similarly, their volumes, initial and final, and they can be in whatever units make sense, but they do need to be consistent throughout your work. So in our example, we've got 1 liters of a 80% stock solution, and we want to dilute it down to 5% by volume, and we need 100 mils. So I state M1 is 80%, V2 is 100 mils, M2 is 5%. Notice that the 1 liter isn't really useful unless we end up coming with a need to have more than a liter of stock solution, in which case we would have a problem, but otherwise it doesn't play into our calculations. So we plug into the formula, solve for V1, we get 62.5 milliliters. Notice that it takes on whatever units we had for V2. But we're not quite done. We still need to describe what to do to make this solution. So we measure out 62.5 mils of stock solution, and we're going to do this with a graduated cylinder. You'll need, typically it's probably going to be a 100 mil graduated cylinder. And then pour that measured amount into a 100 mil volumetric flask. Then dilute with distilled water to the mark on the neck of that volumetric flask. The exercise is similar, but I am more specific. I tell you what you have available to you, and I also ask you to do a serial dilution. This is necessary because I'm asking you to take an 8 molar stock solution to a 0.1 molar concentration. I only want 50 mils. Well, there's 2 ways you could do this and maintain the initial 3 digits, 3 significant figures of accuracy. You don't want to get rid of all of that. Well, you could just make a ton of this, and that would require a great deal of that. So you could measure out, maybe 20 mils, and you could do that with a good deal of precision, and then dilute it down, and you'd end up with a ton of your final solution. But then you could take 50 mils of it, and you'd have what you want, but you'd have a lot of extra, so that's wasteful. The goal here is to avoid that, and so you avoid it by measuring out a smaller amount of your solution here, and your goal is to make not a 0.1, but maybe you make a 0.8 molar solution. So, and then you take a portion of that to make your 0.1 molar. So you take the result of one dilution and feed it into a second. Okay. That allows you to maintain the precision of your dilution, so you can know what the final concentration is, but also avoid some of that waste. Now, oftentimes you're going to use stoichiometry with molarity, and here's some tips. Write M, capital M, molarity, as moles of whatever the solute is over liters. And secondly, if volume is in milliliters, you can often carry that M through the calculations, or you can convert it to liters and then back to milliliters at the end. So this question gives us the balanced chemical equation for metallic zinc reacts with aqueous hydrochloric acid. It wants to know what volume of this concentrated hydrochloric acid in milliliters is required to convert 11.8 grams of zinc to products. So we start off with a mass of zinc, convert that to moles using the atomic mass of zinc, convert moles of zinc to moles of hydrochloric acid by using the stoichiometric ratio. For every 1 mole of zinc that reacts, it's going to need 2 moles of hydrochloric acid. And then convert that into liters by using the concentration. So 2 moles of hydrochloric acid cancels out with the moles of hydrochloric acid there. It leaves us with liters. Multiply by 1,000 to get milliliters. And we get our answer, 144 milliliters of 2.5 molar HCl. So that's around a cup or so. A little bit more than a cup. Okay. The exercise is similar, but it's if you combine 75 mils of 0.350 molar HCl, so a more dilute, and excess of sodium carbonate, so lots of sodium carbonate, what mass of CO2 in grams is produced. Now, notice there's 2 chemical equations given. We're going to use the second. The first one just states that there's an intermediate product. Carbonic acid is the acid that makes sodas fizzy. So when you put CO2 in water, CO2 and water can combine to form carbonic acid. And then when the pressure above the solution is released, CO2 is released. So that's what we care about. And another example, we have a 25 milliliter sample of vinegar, which doesn't matter how big the sample is in milliliters for this question, but it contains the weak acid acetic acid, and it gives us the formula. It requires 28.33 mils of a 0.953 molar solution of sodium hydroxide for titration to the equivalence point. So the equivalence point is when there's an equal moles of sodium hydroxide and acetic acid, one completely reacts with the other. So we start with 28.33 mils of this sodium hydroxide. Convert into liters. Convert that into moles by using the concentration. Note that 1 mole of acetic acid reacts with 1 mole of sodium hydroxide, so this is a 1-to-1 molar ratio. And then convert that into grams by using the molar mass of acetic acid, which I've calculated off to the side here. Multiply this across. Notice that if you're multiplying along the top, that's multiplication. Anything on the bottom gets divided. And that will give you 1.62 grams of acetic acid. The last question exercise is similar. Ask what volume of 0.750 molar in milliliters is required to react complete with 1 liter of 2.25. So for this, you could start with liters and then just convert to milliliters at the end. All right, good luck, and I will see you later.